Alright, welcome to lesson 2. Here we're going to look at some special cases of tangency for implicitly defined functions. Let's go ahead and get started. Alright, so let's go ahead and get started. None of what we're doing today is really all that new, to be honest with you. And so you should have no trouble whatsoever sort of going through and applying some tools that we've used previously to this sort of new situation. So if you have a curve defined as such, go ahead and go through parts A, B, C, and D on your own. You should be able to sketch this curve on your own, but if you need to, go to wolframalpha.com and use that to graph this equation here. All right, so the first thing I want to do is find the derivative of y with respect to x. And so I'm going to need to implicitly differentiate here by differentiating both sides. So I'll go ahead and do that. And when we are all said and done, we find that the derivative of y with respect to x is given by x over y. And what this means in terms of the graph of this equation, or the curve that we get when we satisfy this equation, is that this is, just like we've interpreted the derivative the whole way through, is that the derivative represents the instantaneous rate of change, or the slope at any point along my curve. So if I go ahead and pull up the curve here, and I'm very bad at drawing circles, so I had Wolfram Alpha draw this one for me. But this is just a circle of radius 5, which is what I get when I pick all the x and y values that satisfy this equation here. And if I were to pick any point along my circle, I'll pick that one, any point x comma y around my circle, then dy dx evaluated at this point will give me the instantaneous slope, or the instantaneous rate of change, or in other words, the slope of the tangent at that point. So now when I'm thinking about where my graph will have a horizontal tangent or a vertical tangent, I can sort of go around my curve and just envision what the tangent will look like at those points. So as I rotate counterclockwise around my curve, I notice that once I get to the top of my circle here, the tangent seems to be horizontal. And if I continue then to rotate around, I might notice, I might want to stop here and say that's the only point, 0, 5. We'll just label it 0, 5. All right, but if I keep rotating around, I'll notice that there's another point down below where the tangent is also going to be horizontal at 0, -5. And if I do the same for the vertical tangents, I notice that right here at 5, 0, the tangent to the curve appears to be vertical. And then again, on the opposite side, at -5, 0. So those are the points at which I'd expect my tangent either to be vertical or horizontal. So what we'd like to do now is corroborate the graphical findings, what we discovered just by looking at the curve, with our algebraic representation of the slope of the tangent, or the instantaneous rate of change along my circle. So what you want to do is now use our equation for the derivative to prove that these points actually have either a vertical tangent or a horizontal tangent. All right, so we'll start off with the horizontal tangents, and if I want to prove that the tangent at this point 0, 5 is in fact horizontal, well then I need to show that the slope is 0. So to find the slope at this point, I will use my derivative that I've already found, and the derivative of y with respect to x at the point 0, 5 is given by 0 over 5. And 0 divided by anything is 0. So here, the slope at this point, 0, 5, is in fact 0, which means I'll have a horizontal tangent. And I could do the same thing at this point, 0, -5. And notice that if I do that, I'll get 0 divided by -5, which is again 0. And so this 0 is also the value of my derivative evaluated at 0, -5. So I've shown now that these 2 points have horizontal tangents, and now I want to show that these 2 points have vertical tangents. So the first thing that I want to do is evaluate my derivative at the point 5, 0, in other words, find the slope at this point. And to do that, I will have to take 5 and divide it by 0. But notice that this is undefined. And since it's undefined, that means that I can't define my slope at this point. In other words, it's going to be a perfectly vertical line, and therefore I've proven that at this point 5, 0, the tangent is vertical. And if I went over here at -5, 0, I'd run into the same problem. I'd end up with -5 over 0, and so the derivative evaluated at this point, which I'm not going to actually write out, is also undefined. And what this illustrates is something that we've used over and over and over again, which is if we are looking for horizontal tangents, that means we're looking for a point at which the derivative is equal to 0. And if I have a derivative that is a rational expression, well, then we know to make that 0, we're looking for where the numerator will be 0. And similarly, with a vertical tangent, we know that we want the derivative to be undefined. So if we're looking for places where the derivative is undefined, we're asking ourselves what will make our derivative, in this case x over y, undefined, and that will be where my denominator is 0. So let's actually think about, imagine we didn't have this graphical situation. Let's just say the question said, can you find all the points where your tangent will be horizontal? So if I'm trying to find all the places where my tangent is horizontal, that means that I want my derivative, dy dx, I want it to be equal to 0. All right? Well, that means that I'm setting x over y equal to 0. And when I take a look at this situation here and I'm trying to solve for x, well, I can multiply by both sides on by y, and I'm going to get that x must be equal to 0. All right, well, that's great. I know that the derivative will be equal to 0 whenever x is equal to 0. But how do I know what the y value is there, right? Because I'm trying to find the points, and so I need the y coordinate as well. Well, if x is equal to 0, how could I find the corresponding y coordinate? Remember, I have this original equation. And so by plugging this value of x back into my function, when x equals 0, I have 25 is equal to y squared. So taking the square root of both sides, I know that y can then be equal to positive or negative 5. So the 2 points at which I have a horizontal tangent will be x, 0, 5, and 0, -5. Those will be my 2 points where I'll have horizontal tangents. Now, if I wanted to do the same thing for vertical tangents, here I'd be looking at my derivative and asking, where is it undefined? In other words, where is x over y undefined? Well, that's going to be when y is equal to 0, because this is the denominator. So when y is equal to 0, I will have an undefined slope. Okay, well, now I know that y has to be equal to 0, but how do I know the corresponding x value? Well, if I know that y is equal to 0, I can plug that into my original equation, solve for my x value, which will be either positive or -5, just as we got here for the y value. So the points at which my derivative will be undefined are where we have an x value of positive or -5 and a y value of 0. So we can go either way, and if we don't have the graphical representation, we can still find these places where we have either a horizontal or a vertical tangent. All right, so if we are trying to locate points where a curve has a horizontal tangent, then what we're doing is we're taking the derivative, we're setting it equal to 0, and we're solving. Now, notice there are a couple things I want to point out. First, we're locating points. Now, a point has an x and a y coordinate, so I can't forget that. And so what I'm doing when I'm setting my derivative equal to 0, sometimes my derivative, when I'm solving implicitly, or taking the derivative implicitly, will have both an x and a y involved. And so what I'll have to do is I'll have to solve for one of them. Sometimes it'll be easier than others. Maybe it'll just be really clear, as it was in the first example, that if I want a horizontal tangent, x has to be equal to 0. But there will be times where you actually can choose whether to solve for x or y, and then you'll choose to solve for one of them. Maybe you'll solve for x and it'll be in terms of y, and then you'll need to use the original equation to find the other coordinates. So, in our example, we found that x was equal to 0. That would make the tangent horizontal. And so then we plugged 0 back into our original equation to find the corresponding y coordinate. And we actually got that there were two y coordinates that satisfied that situation. And so we had 2 points, each with the same x value, but different y values. And so we were able to locate 2 points. And of course, locating vertical tangents, points where those occur, is similarly easy. So for vertical tangents, again, we're going to be solving for an x or a y value at the very beginning, right? We're going to find an x or y value that will make the derivative undefined. And in almost all situations, that means we're going to set our denominator, we'll have a rational expression, and we'll set the denominator equal to 0. Solve for either x or y as we would do for a horizontal tangent, and then once we've solved for x or y, we're going to find the other coordinate by using the original equation. So just go back to this step here. All right, so let's go ahead and try this in a couple of different problems. All right, so let's take a look at this problem, and what you want to do is tack this first on your own. And as we talked about when we looked at those AP free response questions, it's really vital that after reading the question and making sure you understand the question, that based on that understanding you come up with a plan. Here's what I need to do, then I'll do this, then I'll do this. Even if it's not written down, just so that you know what your course of action is going to be before you actually start acting. That way, once you've squared away the thoughts in your head, you'll just be able to go, actually start doing it. And that'll make your life a lot easier, a lot more efficient, and will maximize the number of points that you'll be able to get on the AP test. So go ahead and try this on your own first, coming up with your own plan, and then we'll talk about it briefly. I'll talk through my plan. Maybe you can pause again and go back, and then we'll look at the solution. The nice thing about this problem is that it really kind of gives me a step-by-step process for what I want to do. If I notice in part C, I'm going to find all the points at which the tangent is vertical. And if I go back and look at parts A and B, in part A, I'm writing an equation that represents the rate of change of the curve. In other words, a function that represents the slope at any point, or the derivative. And that's what I'm going to need first to write the equation for the tangent at this point, because I'll need the slope at that point. And then for part C, because I'll want to find where that instantaneous rate of change or the slope of the curve is undefined. So I'm actually just going to go through part A and use what I got in part A to find the slope at 1, 2 and write the equation for the tangent. And then for part C, I'm going to set that equation that I got equal to, or not equal to, but I want to make it undefined. So I'm going to, if I get a rational expression, I'm going to set the denominator equal to 0. That would make the whole function undefined. All right, so as you can see here, I'm going to differentiate on both sides. And once I do that, I'll differentiate implicitly, of course. So I'm treating y as a function of x. And so when I take the derivative with respect to x of y squared, I'm going to take the derivative of the outside, 2y to the first power, and the derivative of the inside, which is y, so y prime. And then here I have everything in terms of x, so it'll be 3x squared plus 6x. And now I'm going to divide to isolate my derivative, and I'll get that y prime is equal to 3x squared plus 6x divided by 2y. All right, so that's going to be my answer for part A. And then in part B, I'm going to go ahead and find the slope at this point 1, 2, and use that to write my equation. I go ahead and substitute in the x and y value into my derivative, and find that the derivative at the point 1, 2 is 9/4, so that's the slope at that point. And that means that my equation that I'm looking for is going to be y minus 2 equals 9/4 times x minus 1. And you could go ahead and simplify that through if you want, but this is perfectly fine. All right, so now for part C, I want to find all the points at which the tangent is vertical. So again, I'm going to set my derivative. I want to set it to be undefined. Well, if this is going to be undefined, that means that the denominator needs to be equal to 0. So that means I'm going to set 2y equal to 0, and that, of course, will occur when y is equal to 0. So now I have a y value. I've solved for y here. And notice that that's sort of been chosen for me based on what the derivative is in terms of. I didn't have a choice to solve for x or y because the derivative is going to be undefined only when y is equal to 0. It doesn't matter what x is. So now that I know y has to be equal to 0, I need to find the corresponding x value at which y will be equal to 0. So I'm going back and I'm looking at my original equation, and I realize that I can solve for x if I substitute in a y value equal to 0, which is exactly what I want. So substituting in 0 for y, I'm going to get 0 equals x cubed plus 3x squared. And when I'm looking to solve for a polynomial set equal to 0, I'd love to factor. In fact, when I'm setting anything equal to 0, I'd love to factor. And I can pull out an x squared from both of these terms, which will give me x squared plus x times x plus 3. And then I can look at each factor independently. So what will make x squared 0 is when x is equal to 0, and what will make x plus 3 0 is when x equals negative 3. So now I know two x values at which y is 0. And so that will give me 2 points at which the tangent is vertical. Because the tangent, the slope will be vertical whenever y is 0, and when y is 0, I have 2 corresponding possible x values, which will give me 2 points. So the points are 0, 0, and negative 3, 0. At those 2 points, the tangent to the curve will be vertical. So notice how I'm simply following through with what we've discussed this whole time about vertical tangents, which is that the derivative has to be equal to 0. The one wrinkle here is that my derivative is usually in terms of x and y, so I will actually need to use the x or y value that I found and plug it back into my original function, or not function, but my original equation in order to find the corresponding, in this case, x values for the points. At this point, go ahead and move on to the homework on Math Excel 5.02.